reduction reaction in fuel cells. I'm gonna speak a little bit about the importance of this reaction for energy application, and show a new technique that we have developed in my group that can actually shed light on the reaction itself and the mechanism of this reaction. Now, oxygen reduction is probably one of the most studied reactions in science, I would say, in chemistry for sure. Not just by chemists, I'm a chemist, I'm a physical chemist, but also by physicists and material science scientists, and on and on. But I'll show you that sometimes it's a good way of looking at science through different pair of glasses that will enable us to reevaluate the things that we believe in and challenge some of the paradigms that we all kind of got used to. And to start with, I will start with the motivation. This is the motivation actually for everyone who is dealing with renewable energy today. We need a lot of energy, but to do that, we burn fossil fuels that releases CO2 and other contaminants into the atmosphere. We are facing a global crisis much more severe than the corona crisis in terms of influence, long-term influence. And here there is no vaccination that can help us. We're talking about global warming due to global heat up and our usage of modern life, energy and other emitting sources of CO2, which all ends up with catastrophes such as forest burnout. You see that forest burnout, and everyone have heard about the huge fire in California today, and actually all over the world. The implication is huge. Sorry. So essentially, we're talking about, if we look at the CO2 emission over the last 800,000 years, this research was done by NASA, showing that on average we have a moderate increase and decrease, kind of periodic change in the CO2, while never crossing that dash line. And only in the past few decades, we've already doubled the amount of CO2 from around 300 to or 200 200 on average to around 400. Kind of situation that we're in. It has huge ramifications. Global warming, not just by, this is 0.9 degrees on average on the planet, but it is, in some places it can be 5, even 10 degrees C. Warming of the ocean, again, it looks a very small number, but if you consider the body of water and the mass, it means that it's a lot of heat. And then the shrinking of the ice sheets in Greenland and Antarctica, just in the past 20 or 30 years.
Excuse me, sir.
Yes.
Sir, I cannot see your presentation.
That's strange. No one can see that?
Yes, sir.
Okay. That's too bad. Share. Just a minute. Can you see it now?
We can see now.
Now you can see it?
Yes, sir.
Yes, sir.
Okay. So let me just go a few slides and just remind you of what you should have been seeing. Okay, just a minute. Okay, so we have the global warming, and Here's the graph provided by NASA showing the steep incline in CO2 emission over the years and the implications of that warming on sea level, shrinking of the ice sheets, warming of the seas, acidification of the seas, losing fresh water, rising of the sea level, which will have even more severe implications on our life in the incoming decades. Okay, so
please unmute.
I'll find a way to get everyone. Yeah, okay. So you can see the change of CO2 versus the change of solar activity, because some of the people, especially those who opposes the green energy programs or movements, say that it's all periodic and it's all coming from the sun. We can see that this claim is preposterous. There's nothing behind it. So we're talking about warming due to burning of fossil fuels. So let's have a look at the consumption of energy coming from the consumption of energy according to different sectors in BTU. You can see this is the past here, and that's what is projected for 2050. So we see that the industrial sector consumes the most, as expected. Transportation is the second one, residential, and then commercial. So the energy demand is expected to grow at a rate of about 3% per year in the years 2018 and 2050, which means that we have to install a new power plant of at least 5 to 10 megawatts every day in the world, just to meet the demand of that. That's inconceivable number of power plants. Okay, so what can we do? Well, we will try to find a way of creating energy from renewable sources such as non-petroleum. Now, today, the section of the renewable is about 15% worldwide, whereas petroleum and coal and natural gas takes most of it, 85%. The expectations, if we don't have, let's say, a drastic revolution, that it will grow also gradually and reach around 30%. That 30% is quite limited by the technology. There's no way of storing energy in large quantities that will allow us to go beyond that value, beyond that 30%, say, that we can generate from renewable and so forth. So what we can do is we can either develop a new technology or transfer the extra energy to other countries. I know that there is a project now in Egypt that they are trying to put down a line of electricity between Egypt and Europe. Egypt is a large producer of photovoltaic energy. So if you look at the wind and solar domain and the growth or the sources of energy, we can see that the hydroelectric power generation is by far larger, is the largest section in renewable energy. but this is limited. This is limited by the but what God gave us, what the planet is allowing us to do. So that's going to grow to decrease as the solar and wind will increase, but the total itself is going to increase, as I mentioned in the previous step. Now, what can we do? What can we contribute to this research and development effort? Until we can have 100% renewable from sun and wind, we're still going to need to use the energy coin. Now, the most abandoned energy coin or the energy currency is hydrogen. Hydrogen is all over, and if we can use hydrogen, then we can transfer the energy from one molecule to the other and from one fuel to the other. Now, the advantage of using the hydrogen is not just by taking it and burning it, because if we do any kind of combustion process, we'll end up, as you probably most of you know, with very low efficiency. If you look at this table, this is a table that shows the theoretical and the practical efficiency. So theoretically, a combustion engine can give us something in between 30 and 35% efficiency, 50 to 70, while in practice it can give only 30 to 35, while fuel cell can give 100% efficiency, and in practice not very far. 60 to 70% of the energy of hydrogen can be converted directly to electricity. So how it is being done? The hydrogen passes. This is the device. Fuel cell is a device that can be envisioned as a large battery. Now, in a battery, you use the active material, and then you recharge the battery, or you throw it away if it's a primary battery. In fuel cells, you can take the same battery, and now you can flow the reactants through the battery. While doing that, we're continuously generating electricity. So we have hydrogen flowing through the anode side, and we have oxygen or air flowing through the other side. So the product is the same. In the same case, we have the same product is apparent, meaning it's water, and even if it was a combustion process, it will be water. If we take hydrogen and oxygen, that's the product. That's the product that is expected. The advantage is the ability to do these reactions separately and control the rate of the reaction and the energy of the reaction. We can directly convert the energy of hydrogen into free energy of reaction. So we have hydrogen. The hydrogen decomposes or oxidizes into protons and electrons. The proton crosses a membrane, electrolyte membrane, and reacts with oxygen to form water. To do this reaction, we need catalysts. We need catalysts both for the anode and for the cathode. Now, the all units here, the whole cell, the whole fuel cell, is just one unit. To get a appreciable amount of energy and most importantly, power, we need to pile up few of these cells. You need to connect one cell to the other in series. We call it a fuel cell stack. Here you can see an image of a stack with the fuel cell units in between each stack. Can go up to 20, 50, sometimes even 100 cells connected in series. And the application of that is across the board. Meaning we can use it for space shuttle, or we can use it for small devices. We can use it for car. We can use it for trains, planes, auxiliary power, and a lot of other things. Now, there are plenty of fuel cells. Some of them are can be operated at room temperature, such as polymer electrolyte membrane fuel cell, PMC, that can be operated around 70 degrees C. 80 to 200, while others required much higher temperatures, such as solid oxide fuel cell or phosphoric acid. Anyway, for transportation and for residential use, most of the people will agree, the experts will agree, that the polymer electrolyte membrane fuel cell is probably the best choice to use. So the anode potential is determined by the activity of the protons and the pressure of the hydrogen, and on the cathode, the potential, the thermodynamic potential is determined by the pressure of the oxygen and the activity of the proton and water in the vacuum phase at the end. We define the power density as the power divided by the volume or the mass of the active material. Now, we have few problems in fuel cells that if we will solve them, will make fuel cell a viable technology that can be implemented in most of the known technologies, such as cars and so on and so forth. The main problem of today, or one of the two main problems that we're dealing with today, is the hydrogen storage. We don't have enough for the hydrogen production is still a very expensive process. Now, today, a kilo of hydrogen costs around anything between $11 to $14 a kilo. This is that's way above the $2 per kilo of a gasoline, for example. So there is a big way to go here, and to improve the technology of hydrogen production. Usually, hydrogen is produced from renewable nuclear fossils, and what we call green hydrogen should be coming from electricity, from renewable electricity, renewable sources by electrolysis. Electrolysis is a very inefficient way of producing hydrogen as of today. Now, people are working on it, including us, and hopefully we'll be happy to share some breakthroughs in this area. Now, there are other options to store hydrogen, such as hydrocarbon fuels or metal hydrides, such as sodium borohydride, magnesium hydride, ammonia boron, and so on and so forth. We have been working on DME for the past few years as a hydrogen carrier. And one of the most important parameters in this area is the gravimetric hydrogen density. It is very important for portable applications and for electric vehicles and transportation, because you need to carry these heavy tanks or the system that generates the hydrogen. So as of today, the leading technology here it's here. Sorry, it's compressed hydrogen made of a hydrogen tank made of a Kevlar polymer reinforced with aluminum and so on, and can go up to 700 bars, which is very high pressure, and in the view of some people, even a very dangerous technology. As all of you are aware of, that hydrogen is not easy to handle, and it's highly explosive, and despite the fact that it contains a lot of energy. So by compressing the hydrogen, by the way, we're losing about 15% of the energy content of the hydrogen itself, the fuel. So that also should be taken into account. So people are looking for different alternatives or more advanced way of I'm still being hands on different materials research area in this arena. Okay, so that was the first main problem, the hydrogen. The second problem is the cost of the fuels. And the cost of the fuel cell, this is a breakdown of the cost. As you can see that the major cost of the fuel cell is coming, the expense is coming from the catalyst itself. If you remember, we have catalysts at both electrodes. Now, most of the catalyst goes to the oxygen and not to the hydrogen. Hydrogen is a quite fast reaction, but oxygen is a very slow reaction, as I will mention in a minute. But the problem is that the catalyst is made of platinum in this type of fuel cell. Now, platinum is a very expensive noble metal, and probably if we go for worldwide production, it will not be sufficient to support all the activities, even if we had the money. We can print out more money, but we cannot make more platinum. So we're kind of stuck with the best catalyst, but with the limited ability of using. So there is an extensive effort to find alternatives. Look at the platinum cost. This is just an overview of the cost, and 80% of all platinum in the fuel cell is placed in the cathode, in the oxygen side of the fuel cell. So we need to solve the oxygen problem in the fuel cell. So the catalysis, we need to improve the catalysis of the oxygen reduction in the fuel cell. So why do we need to do that? So here's the list of some of the shortcomings of oxygen reduction. The activity, the exchange current density, which is a measure for the kinetics of the reaction, the I0 is 10 and minus 8, versus if you compare that to hydrogen, is 6 orders of magnitude higher than that of the hydrogen. The price and availability of platinum we have discussed, $30 per gram changing, and around 40% of the fuel cell cost. And platinum loading is 5 times higher in the cathode, and given all these, there is a severe problem of durability of platinum over time. It appears that at high potential, gradually, even though platinum is considered a noble metal that will not corrode, it corrodes over time, and there is a loss of material, a loss of surface, and that limits the lifetime of the system. The expected time is around 8,000 hours of continuous operation, and everyone is below that. Okay, now we're in the window into it's been studied for many years. To simplify this very elaborated description of oxygen reduction and steps and so on, I will just say that there are 2 main paths: hydrogen from O2 and another 2 electrons. Sometimes the hydrogen peroxide can release from the surface and go and diffuse into the solution. That way we can embed into the tip, into the AFM tip, or to another microelectrode tip. We can embed an electrode, and then we'll have a sort of a shuttle reaction: oxygen or oxide going into reductant, and reductant goes to oxidant. We can do that reversibly, and so as we go closer to the surface, the current increases. That way, we can scan the surface, we can move it over the surface and measure the reaction, the reaction that we're interested in as a function of position across the surface. Everything is connected. The movement is controlled by a piezoelectric controller, and so on and so forth. So we're talking about things. This slide actually compares few measurements we call SECM. Compare that with scanning electrochemical microscopy with the method that I've just described, and the method that we've been working on, electrochemical microscopy combined with atomic force microscopy. It's called SECM-AFM. Now, the problem with the SCM is that there is a bias between the tip and the surface. So, and the distance is very narrow. It's 2 nanometers. But you cannot control a reaction and control the distance at the same time, because the control loop is controlling the distance by measuring the current. Now, if you measure both the position current and the reaction current, you have a mixed current. So you can never tell whether the abrupt increase in the current is coming from, let's say, a particle, or it is because there is a change, or from the reaction, for example. So this method is not suited for reactions. The problem with SECM is that we have to keep large distance from the surface, because it has to be at a constant distance from the surface. Otherwise, we'll run into the same problem as with SCM. We need to separate between the position, the current that controls the position, and the current that comes from the reaction. While in AFM, the position, if we use, this is now our method, we use the force modulation to position the tip, and we use the inner electrode to control the reaction. So we have 2 measurements at the same time, both position or force topography, so we can get much better resolution, because we can do that at a distance of around 4 nanometers from the surface. So here is an image of a tip. The inside, this is the platinum wire embedded in silicon. The diameter is around here of the platinum. We set up an interesting setup. We just took the electrode and the catalyst, put it on an HOPG. We have a laser, we have a photodiode, we have the electrochemical cell. The dots here down are the platinum particles or the catalyst particles. Everything is connected to a potentiostat, and we have a reference electrode and counter electrode to complete the cell, the electrochemical. Here's how it looks like. This is the cell. The inner side is the highly oriented graphite electrode. Here we have a tiny gold wires that connect, and we have a silver wire as a reference electrode and a platinum wire as a counter electrode. This is the AFM machine. We place it over a air floating table, and this is the basic step. At first, what we did is we wanted to see if we can control the reaction. So here is an empty carbon electrode, HOPG electrode, and we put a platinum solution into this, on top of that electrode, and we were able to direct the deposition of platinum by applying potential. Here you can see that the differences between nitrogen, which is and oxygen, or this is before, this is the bare HOPG and the platinum. So we saw that there is a slight oxygen reduction even on HOPG without even having platinum. Now this is not, it didn't come as a surprise, because there is a branching in science in this area that deals with non-platinum electrodes that can do oxygen reduction even without platinum. These materials are based on carbonized materials, different modification of graphitic structure and non-graphitic structure that allows oxygen reduction. But very little is known about these reactions, despite the fact that we've been studying it for the past 10 years, not just us, all over the world. So we took it one step further, and we were able to deposit platinum as we wish while scanning the surface, and you can see a very nice alignment of the platinum. The reason for this red dot platinum, the reason for this alignment is the fact that while forming these particles, we also drag them using the tip. The tip is dragging the platinum to the end. We can control the size of the particles by controlling the and the dispersion, by controlling the molarity or the concentration of the platinum salt. Then we set ourselves, well, measure not just the oxygen reduction on a single particle, but we want to measure the reaction also of byproduct. To do that, we had to modify a little bit the setup, and we went from 3 electrodes, meaning the electrode down here, the HOPG, and a silver reference electron. We had to add a secondary electrode. And the reason for doing it is because we could scan the electrode and see the oxygen reduction, and then repeat the same measurement and scan the. So here's an example. You can see on the left side, on top left side, you can see an HOPG, highly oriented graphite plane that was freshly. You can see an edge plane here. The A is at A. It's an edge plane of the graphite, and this is an AFM image. Now we can take the tip, and this is the electrochemical part, and now scan and see where we have electrochemical currents. So here, the dark areas is where we're getting electrochemical currents from the surface. You can see that most of the current is coming from the edge plane, and perhaps some defects here. And then we run the same experiment. At this time, we were looking for hydrogen peroxide. We took the tip and we placed a specific potential that only hydrogen peroxide can react. And quite nicely, we can show that the hydrogen peroxide is formed at the same location. You can see the currents coming from the same location where oxygen reduction takes place. So this is a direct proof that the hydrogen peroxide is connected directly to the formation of oxygen reduction product. You could also see some stretching and so on and so on. Now, we took this surface and we exposed it to nitrogen plasma, cold plasma. And the reason for wanting to do that is because in the literature it is widely described the effect of nitrogen dopant on graphitic or Sc2 carbon on the oxygen reduction. Namely, that if we can embed nitrogen atoms or create defects on the surface, we can enhance the activity of the catalyst. And this is exactly what we did. You see here that there is certain etching of the S-plane, but look what happened. All the surface out of the sun becomes active. And if you look at the hydrogen peroxide, it follows the same pattern. The only difference is everyone that looks at it will say, well, here you have 500 nanoamps as current, but here the peroxide, this is peroxide mapping. The peroxide gives you higher current. How can it be? How come the product can be more than the reactant? And the answer is that for measuring the product, we're using larger electrodes. We're using a larger counter electrode. We're not using the tip. For oxygen reduction, we're using the tip as a counter electrode to probe exactly above that. While for the peroxide, we're only sensing. So we're not sensing 100% of the peroxide. We're sensing part of it, but even that part of it that is generated by a larger counter electrode gives us higher current. Now, a second step or a third step will be to, again, to dope it with some other atom or element. And in this case, we use iron. And you can see the iron effect adhering to the same active site or hotspot that was previously doped by the nitrogen and gives us higher current. That was published 2 years ago right now. One can say, well, how do you know that this is oxygen reduction? So here is Here's an experiment using argon, and as you can see, the currents are significantly lower. And this is even more important. This is the immersion of iron without N2, before doing the N2. You can see again that we're losing all the activity throughout the. Now we've dedicated a lot of efforts to studying the mechanism of oxygen reduction. We've proposed different mechanisms that include atoms of iron and cobalt and structures doped with nitrogen and so on and so forth. And you can see that was published in Chem in 2017. You can read that throughout the period. Okay, so but that wasn't enough, and the reason is because we wanted to know that we're measuring exactly the peroxide that is generated from the reaction. And the reason for wanting to do that is because we have to add up everything. We have to know what we're measuring and to add up the different reactions. So here's another experiment that we've run. This is on a single particle of a size of 160 nanometer. This is a platinum particle. And you can see that most of the current is coming from the center, and you can see the peroxide is smeared all over that. So the resolution with peroxide follows to some extent that of the oxygen reduction, but not entirely. And the reason is, again, because it's done in two different reactions, two different experiments. Here is an agglomerate. The poisoning of the surface would result in the same outcome, the same image. You see here is 40 nanometer. This is 40 nanoamps, and this is 3 pico. If it was in the same region, then it would mean that we're not measuring oxygen reduction. We're measuring something else, and that's a direct proof that we're indeed measuring oxygen reduction on that single particle of around 200 nanometers. Here's measuring the cluster and the supportive catalyst. We can say exactly where the catalyst is located over a carbon support. Different locations, different spots, and this is just by looking at the oxygen mapping. If you look at the image, for example, this is the AFM image. You cannot detect where the oxygen or where the platinum is. You see here 2 particles. You see here this can be carbon or something else. But when you look at the dark spots here, these are for sure platinum catalysts, and we can identify exactly where the catalyst comes. So most of the current is coming from these spots, but the utilization is low. So as I mentioned, we wanted to measure both the oxygen reduction and the hydrogen peroxide at the same time, not by 2 different experiments, one after the other, but at the same time. To do that, we have designed a different tip. We took the old tip and we coated it with gold. This is a gold of around 80 nanometers. And now we can do both. We can do the reaction with the tip, using the tip as a counter electrode, but detect the hydrogen peroxide on the gold, on the surrounding gold. So we are using it to do 2 functions. First we calibrated it with the ruthenium salt, and then here's the image of the gold coating over the tip after it breaks down. Okay, this is the cantilever, and we measured. This is the ruthenium, and one of the things that we wanted to see is what happens if we approach the surface. So here, this is what we call the tip approach. We took the tip and we put it closer and closer to the surface. And you can see as you go very close to the surface, 50 nanometers and below, the current suddenly jumps to very high current. And we see the redox, meaning if you look at the redox reaction. So we took that, and now we wanted to compare the old methods with the new method. So we took an HOPG, okay, and we scan it with the old method, what we call the dual electrode. One measurement for the oxygen and one for the peroxide, and this is the peroxide side result. We can see the reaction. We can see that the currents are around 70 nanoamps, whereas if we do it with the gold-coated tip, the new method, we get a smaller current, but very high resolution. You can actually detect between individual edge planes of the carbon. So here's another experiment, now with platinum. You can see you have 1, 2, 3, and we have another 2 small particles just lying around next to the particle number 1. And each particle is around 100 nanometers, meaning the larger and the smaller are even smaller than that. And now we scan the reaction again simultaneously using the gold-coated tip. And as you can see, according to the contrast, it's a very high resolution image. The whole bar here is 200 nanometers, so we're looking here at around 20 nanometers. Now, a full scale is 20 nanometers. We can even detect smaller parts of this tiny particle. And we can get, and here you can see that the peroxide follows exactly the same pattern as the oxygen reduction. There's no smearing effect. The peroxide stays in the same location. So the interesting thing is that now, perhaps even before moving to that, now if we look at the current, the current here is 15 nanoamps. The oxygen reduction. This is the oxygen reduction. Now, if we look at the peroxide is 9 nanoamps. Now, 9 nanoamps is lower than 15 nanoamps, but it's certainly not zero. This is closer to 80%. Now, if you remember, we have said at the beginning that the reaction on platinum surfaces is agreed by everyone that it is a 4-electron reaction, meaning a direct oxygen going into water. Now, if this is the case, if indeed, then we should have seen even smaller or much smaller values of peroxide. We should see 0 value of peroxide. But bear in mind that here we're seeing most of the current goes through the hydrogen peroxide formation pathway, not through the oxygen reduction pathway. And this is counter to what everyone else believes in for a very long time. But moreover, we can see that by using the platinum, we're using only fraction of the activity of the platinum. Here on particle number 1, for example, we're using only 38% of the surface of the platinum. Particle number 2, 70%. So if we can improve that utilization, we can improve the platinum. We can reduce the platinum content in the fuel cell. We can still use platinum, but at a much lower content. Now that we know that we're utilizing so little of the platinum that we put in. And the last step was to look directly at the peroxide. Now, the peroxide is so important, we should be able to detect it. So we have applied a near field effect, what we call the tip-enhanced Raman spectroscopy, where we take we put the whole cell under the Raman microscope, and then we use a 532 nanometer laser to shine the edge of the tip. Now remember, the edge of the tip is made of gold. It's coated. It's a glass coated by gold. So the gold acts as a plasmon enhancer, and so that what we have here, we have an enhancement of the Raman signal. Or in other words, we can detect the Raman signal or the absorption right under the tip of the AFM, the gold tip. So here's what we get. You can look at this is just looking at the in carbon, plain carbon, no defects, nothing. And we can see that we have no peaks, no significant peaks at different distances. Even as we go towards the surface, we have no peak of peroxide. Whereas if you look at the defects here, we know that now that the defects create more oxygen sites. We see that as we go from 1,000 nanometers to 4 nanometers, this is 4 nanometers, we can enhance significantly hydrogen peroxide, hydrogen peroxide detection. So this is a far field, and as we go further, this is the intensity of the peak. The peak grows significantly. We were able to calibrate it. We took different concentrations of solution of peroxide, and we're able to get sort of a calibration curve just by looking at the increase of the heat of the Raman, a different concentration. This is 10 molar down to 2 molar, and here is a fraction below 1 molar. So the next step was to measure all 4 things simultaneously. We can measure the topography of the HOPG, of the electrode. We can measure now the oxygen reduction at different locations with a spatial resolution of around 20 nanometers. We can measure the peroxide formation here of the same unit area, and now we can also measure the peroxide itself, the intensity of the peak that comes. So the purple, it means high concentration. Purple and dark is high, and yellowish and reddish are lower concentration. And when we compare the concentration, the expected concentration from the electrochemical process, and by using just Faraday's law, and comparing it to the adsorption, we can see that we get the same concentration. That means that under the tip, we were able to measure 0.5 molar of peroxide. It's much more than you would expect in the solution, but under the tip, the concentration due to diffusion increases significantly. Then we again transpose that into platinum and measure again. Here the resolution is less observed, but indeed we were able to show that the same behavior here. So what do we understood from that? We understand that everyone else thinks that platinum is for electron reduction catalyst. It takes oxygen, 4 electrons, 4 protons, and directly transform it into peroxide, into water. While in our case, we measured and we saw that most of the current is assigned to peroxide formation, to the 2 electrons, 2 protons, and then peroxide that turns into peroxide, and then peroxide into water. So how can we bridge this frequency? The idea that to understand that we need to understand how those people who measure or claim to measure for electron reduction reach that conclusion. They use a technique, an electrochemical technique that's called rotating ring disc electrode. You take your material, you have a disc in the center, and you have another ring surrounding that. You have a small insulator, and then you take and you rotate the electrode around an axial shaft, using an axial shaft, and you measure the current that comes from the center. And if you have peroxide, then the peroxide is thrown out towards the outer ring, the outer electrode, where it can react independently. So here is the oxygen reduction, and here is the peroxide oxidation. So knowing the collection efficiency and everything of that electrode, you can measure the amount of peroxide that is emitted from the central electrode, from the platinum lying here at the center. But this is a macroscopic kind of analysis. And the reason is because when doing it, we're placing a thick layer of platinum, many billions, trillions, who knows how many, of catalysts on the surface, one lying on top of the other. And as you do that, if the peroxide is formed, say, inside that layer, it can continue to react within the layer. So eventually, what comes out is only water, not peroxide. You make high oxygen to hydrogen peroxide. The hydrogen peroxide can further react on platinum and goes out as water. So practically, everyone measures just water with very little peroxide. But if they were able to measure an individual particle, they would see that most of the reaction is a 2 electron plus 2 electron reaction. And indeed, this is what that was reported somewhere else, showing that if you increase the loading of the catalyst on the electrode, if you increase the thickness of the electrode with the thickness of the platinum layer, you get hydrogen peroxide. So what is the take-home message? We were able to show a new approach for studying catalysts, electrochemical catalysis simultaneously in a way that was never envisioned before, never were able before, in a very high resolution. The results clearly show that the graphite edge plane is responsible for oxygen reduction. This was assumed but never seen before. Everyone knows that some defects can improve. It was shown before, but seeing it in your eyes and seeing where exactly and which defect belongs or which defect actually promotes more the reaction, that was not seen. Now, the counter to previous microscopic reaction, we now understand that the conception that oxygen reduction is a 4 electron direct reaction is incorrect, and the textbooks should be changed to accommodate the fact that it's actually 2 electrons plus 2 electron reaction. Now that leads us to just a few examples of what we've been doing using this approach. We're developing, first of all, carbon-based catalysts, molecular catalysts, based on Corot. That was published long ago, but still a highly cited paper showing a molecular catalyst that is stable in acid solution and can reduce oxygen efficiently. We're able to take similar molecule and create very interesting, highly loaded catalyst with a lot of nitrogen in it, and measure the basic properties of this by using a high pressure a method that we've developed alongside with Professor Ariel from Ariel University. Then we have developed a way using a cold plasma to introduce defects into CNTs and other graphitic structure, showing enhancement of oxygen reduction even without using any metal to do the reaction. And this is very important. This is a completely metal-free catalyst. And then we took the plasma and we activated the catalyst support, and then show that it's becoming even more active towards oxygen reduction using a different precursor, CNT, or taking it after the formation of the catalyst and exposing it to nitrogen plasma, showing again a very pronounced enhancement of the activity. Again, no platinum at all. So just let me thank the people who pay my tribute. Srikanth, who did he's already in Dublin working on postdoc work. He did the AFM work. Kalan did some of the carbon material and the modeling, and Rupati Mohan was just graduated she did the synthesis and the analysis of the advanced carbon material. That we think this is some of the group. Obviously, it's not updated, but we need to find time to take pictures. It's difficult to bring everyone together in Corona times. A little bit about the university. This is Ariel University. We are located here in what's called the West Bank, halfway between Tel Aviv and Jerusalem. This is Tel Aviv. Here's Jerusalem. So it's we are the top of this triangle, about 50 minutes drive from each one, or even less, 40 minutes drive from Tel Aviv or from Jerusalem. And obviously this is Jerusalem and the old city, and you're all welcome to come once we can afford that. Hopefully soon enough we'll have a vaccination and everyone will be happy. I'd like to thank my provider, the ISF, Israel Science Foundation, Ministry of Energy, Ministry of Defense, Ministry of Commerce, Ministry of Environmental Protection, long list of students and postdocs and PhD students, MSc, and many in the future. And thank you very much.
Thank you, Professor.
I really
May I
admire.
ask you?
Yes, many.
Yes.
One.
You may ask your queries in the chat box, or you may please unmute your mic to us.
Just a minute. Let me just stop the sharing.
Yes, Professor.
And now I can see it. Okay. Questions. Want me to read the question? I heard the second one. Perhaps someone else has heard, because your line is not really clear. So, the quantification of the hydrogen peroxide. That's what was the second question, right?
Yes. Yes.
Yes. The way we did it is we took a standard solution that we prepared of hydrogen peroxide, a different concentration, and we placed it
in
the tip without running any current or anything. We just placed the tip as if it was under measurement. Okay, and now we use the laser to enhance the Raman signal, to provide the Raman signal, while shining at the top of the tip, of the gold tip. We get, as the tip approaches, or as we stop, let's say we're at 5 nanometers away from the surface, then the signal has certain intensity, which is now proportional to the concentration of the peroxide standard solution that we use. Okay? So that was the calibration curve, as we did. Yes. On top of that, beyond that, we run the electrochemical experiment. Now, the electrochemical experiment means that we're generating current. So if we can integrate over the current, integrate the time and the current throughout this measurement, we can use simple Faraday law to evaluate or to estimate the amount of peroxide that is formed electrochemically. So that means we know the charge. If we know the charge, we can know how much moles, and then we can take the volume of the gap between the tip and the surface and transpose into the concentration, expected concentration. Now, so we have two ways of measuring the peroxide. One from the spectroscopy and one the chemistry. And interestingly,
so my previous question challenges the context of new generation fuel cells which you are referring to. Industrial challenges.
The industrial challenges are quite immense, I would say. There is no industry of fuel cells. There's very little. There are very few companies that produces fuel cells, and tremendously expensive. We're now talking about fuel cells that cost around $1,000 per kilowatt, which is on a large scale. If you go down, the prices can be even more expensive. But for some application, we can bear that. If we have enough, we have all the solution, but we don't have all the solution, meaning we don't have an efficient way of storing hydrogen. And if we don't have that efficient way, it means that we rely on very expensive, and we're not really storing enough hydrogen as we need. The whole system becomes huge and very heavy as compared to other alternatives that we might think of. So we have to find a good solution, a good way of storing the hydrogen. As I mentioned, one of them is suggested as compressed hydrogen and already implemented in Toyota Mirai, commercially available car run by fuel cell. If you have $60,000, you can buy it. You have to make sure that you have a hydrogen station next to your house. Otherwise, you'll be stuck with the car. People all over the world are working on different alternatives for hydrogen or other future. Yes.
Thank you, Alex.
You're welcome.
Thank you.
Questions? Please don't be afraid. Now I'm very far from you. I can't do anything. Christy Thomas. Sir, thank you for the excellent talk. You talked about reaction and at the cathode side and possible alternatives for platinum. What about replacement of the anode side? What are other possible applications for SECM? Okay, these are two questions. The anode side requires less than 20% of the platinum on the cathode side. Hydrogen oxidation is probably the fastest reaction we know. The reaction rate is anything between tens of milliamps per square centimeter to amps per square centimeter. So that's not the problem. The major problem is the oxygen. The oxygen reaction is very slow reaction. Again, because of the multiple electrons, multiple protons that are involved in it. Now, other application of scanning electrochemical microscopy, actually you can use it not just for energy applications. You can use it for biological applications. As long as you have an electrochemical reaction, you can use that reaction to probe the surface. You can actually, you're using it to probe the topography. You can use it to probe the conductivity of materials. For example, if you have a surface and you have a non-conductive material on the surface, and you scan it now with a certain reaction on the surface, the line that comes from that something lying on the surface will be, the current that comes from it will be zero. So here you know that you have a non-conductive material on your surface. So that's only if you, the literature is filled with that. We are not the inventor of SECM, but if you know Professor Ellen Bard from Houston University, he's the pioneer scientist who invented this method like 20 years ago or even more. Okay. Questions? You can do it by texting or by just unmuting yourself. either it was too elaborated or you didn't understand a thing.
If any,
Yes, definitely. Okay, if there is no other questions, any of you who are video? Yes, let's see. No. So if there are no other questions, I want to thank you all for joining me and allowing me to express my enthusiasm through the Zoom and share with you our results of which are not just my results, but the results of my students and colleagues. And I really enjoyed it, and I hope to see you all. And I hope many of you will join this area, which is highly important, not just for the sake of science, but I think for the sake of humanity. Thank you all, and have a good afternoon, good night, perhaps now. Thank you very much.
thank you, Professor. Now, I request Dr. Angel Susan Cherian, the Assistant Professor of Marthoma College, and the coordinator and a member of the organizing committee to thank the gathering. Thank you, ma'am. I hope you all enjoyed the session. I'm very thankful to Professor Alex Schechter and Dr. Nandakumar Karikal for spending your valuable time with us. And I also take this opportunity to thank each and everyone who implicitly or explicitly became the part of this event. Thank you all. God bless you.